This section deals with what it will take to build trust in autonomous vehicle technology. When seeking public adoption of highly automated vehicle technology, all the road testing and all the simulation and all the engineering rigor and all the other things that can be done on a technical basis won't matter if the public does not trust the technology. Ultimately, this technology will only succeed if public stakeholders, when considering the question, would you trust your life to an automated vehicle, honestly feel that the answer is yes. Don't forget that this question applies not only to the people who are going to ride in these vehicles, but all the other people who are going to share the road with them, especially vulnerable road users. Everyone has to have trust and confidence in the safety of this technology for it to see widespread adoption. To understand the technical requirements for gaining trust through a purely numeric argument, let's consider a hypothetical validation campaign. First, we start with a 10 billion mile simulation campaign. Why 10 billion? Well, that's an arbitrary number, but I assume the goal was fewer than 1 fatalities per billion operational miles, which is a few times better than a typical human. Those billion miles would have to be across the entire operational design domain and include emphasis of appropriate high-risk situations. 10 billion miles is a lot of miles, but if you have enough computers running for long enough, perhaps you could do that. Those simulations have to be fed something, though. So let's say you had 100 million miles of collected data and scenarios. That's likely to be some small combination of road testing, but a much larger fraction of just data collection cars running around with human drivers, making sure that all the edge cases that are at the 100 million mile level have been detected and put into the simulation. Finally, there would be 10 million miles of road testing of the final software, with a claim that this validates the simulation. So what you end up with is an inverted pyramid where there's a positive risk balance claim based on 10 million miles of road testing. But the 10 million miles of road testing aren't to prove it's safe. They're merely to prove that the data collection was thorough and the simulation was accurate. There's 100 million miles of data collection. You'd like more, but at some point there's a limit to how much you can have. And all that supports 10 billion miles of simulation. Now ask yourself, is this statistically valid? Because you're making a claim of 1 billion miles between fatalities based on only 10 million miles of road testing. There'll be questionable confidence in the collected data being representative of what you need for the simulation. There'll be questionable confidence about the road testing validating the simulation. This argument might, in fact, be part of a compelling safety argument. But you need more than an argument of, look at all the simulation miles, look at all the data collection miles, and look, 10 million miles of road testing, because the data collection miles and the road testing miles are not nearly enough on their own to give statistical confidence that this vehicle will actually be safer than a human driver. It's important when performing validation to ask the question what the limits of that validation are. In other words, how much do you trust your validation? Hypothetically, would you put a child in front of a self-driving car in which there were 10 billion miles of simulations, but maybe there was a simulation error that caused incorrect results? Those simulations were based on 100 million miles of data collected, but perhaps there were particular scenarios that you didn't collect any data for. And you did 10 million miles of road testing, but that road testing didn't encounter any of the missing scenarios and didn't happen to detect any of the simulation errors. And you did 10,000 repetitions of various high-risk scenarios on closed-course testing, but you used standard dummies instead of people, and your perception system is really good at finding dummies, but not so good at certain configurations of people. And all that was biased perception training data that maybe had no instances of yellow shirts in it. And all the software, the simulators, and the data collection system and everything was built from software binaries and tools that you downloaded off the web with no safety qualification. The point here is, in addition to making sure your vehicle's software is safe and of high quality, you have to make sure that the infrastructure software that you're using, such as simulations and data collection, don't have systematic errors that will miss potential defects in your vehicle software. Taking a more standards-based point of view, this means you need tool qualification for your compiler and runtime library, also for your simulator, your data collection system, your data management system, your machine learning training system, and so on. Even if your validation results show that your system is acceptably safe, and you've performed robust tool qualification, there's still more required to establish safety. Pure testing and testing alone is insufficient for life-critical systems. There are simply too many possible ways to have defects that are not caught in testing for any affordable amount of testing. That's why safety standards not only require testing, but also require using engineering rigor for computer-based system safety. This means when you say that a system such as an automated vehicle is safe, you're saying not only did you test it, but also that you intentionally used engineering rigor as a basis to create a trustworthy product. Engineering rigor addresses, can you trust the system itself? Is it engineered for safety? Were standards and best practices used? Is there a safety case documenting that all this happened? As well as, can you trust your validation process? Did you engineer the simulations properly? Did you design the validation campaign properly? For example, did you use a reasonable design of experiments to make sure you sampled everything you need to sample during testing? Even if you've used a robust validation campaign and a high degree of engineering rigor, it is unlikely, due to high complexity, that an automated vehicle will be released completely defect-free. It's important to release an automated vehicle with high confidence that it is acceptably safe, but you will never have perfect confidence. The expected risk of the residual system will have both a mean, an expected value, and some uncertainty. You should deploy only when the expected risk is acceptably low, but you need to deal with the uncertainty. Uncertainty includes things such as unknown missed edge cases that you didn't see during road testing, or gaps in the validation plan that you did not realize were there, or unknown unknowns in general. To cover these unknowns, you'll need field engineering feedback. That can be provided by continuous field monitoring. The idea is you monitor safety performance indicators, SPIs, which are specific data sources that you can monitor during operation, not just for the sake of monitoring data, but rather to detect whether or not your safety argument, the reason you think you're safe, is actually true and valid. The idea is that an SPI violation means the safety argument itself has a defect. Either something happened that you did not plan for, or you were expecting a certain arrival rate of some issue and it's coming higher than you budgeted for, and so on. When you get an SPI violation that some value is above a threshold, what that means is your reasons that you think you're safe are no longer true. You need to investigate and fix the root causes before you have a loss event. Continuous field monitoring should start during validation, but continue into and after deployment so that you can moderate the risk of you think you're safe and everything checked out, but now either you encountered something you hadn't thought of, or alternately, the world changed out from under you, and now you're in a different world you didn't anticipate, and the SPIs will inform you that the world has changed and you need to change your system to remain acceptably safe in this new, changed world. An essential aspect of ensuring safety is having a robust, healthy safety culture. Safety culture is about whether you effectively execute your various procedures and technical tasks with an emphasis on ensuring safety rather than just going through the motions. Some aspects of safety culture include the following. Did you do what you said you did? In other words, you said you used engineering rigor, but did you actually use it, or did you skip some steps? Did your validation skip over known problems? For example, did you avoid testing things that you knew didn't work so that your validation could say, yes, we passed all our tests that we ran? Did your engineering team skip process steps that were supposed to be executed for safety-critical software? And along with that, when you executed the process steps, did you actually do them robustly? For example, did you do a peer review of 50,000 lines of code in about 10 minutes? Well, that's not likely to be an effective peer review, even if you did sign off the paperwork saying you performed one. Is your field monitoring ignoring SPI violations? If you see a problem during testing, do you say, oh, well, we can't reproduce it, so that one doesn't count? Or did you record the problem so that if sometime later a different person sees that same problem, they'll know that it actually has happened before and it does need to be paid attention to? Good safety culture mitigates risk. Having a safety management system, SMS, is a start towards that. But safety culture involves everyone in the lifecycle, including design as well as operations. Here's a very simplified description of core ideas behind a safety culture in 2 parts. Part 1. Are you incentivized to do the right thing? If your work environment has incentives to do the wrong thing, then you can expect that to result in a safety culture problem. The second part is it okay to tell your boss bad news? Will you get fired by telling your boss bad news, or does your boss accept the bad news and take it for action to make sure any safety problems are fixed? If your boss punishes people for bearing bad news, that will lead to an ineffective safety culture. The importance of having a robust, healthy safety culture cannot be overstated. When a road test vehicle struck and killed a pedestrian in Tempe, Arizona, Uber ATG launched an internal investigation that showed that the root cause of the problem was an ineffective safety culture. If your company does not have an effective safety culture, you can expect to have unnecessary crashes and unnecessary fatalities. One way to look at all the factors beyond testing and validation that are in play when building a safe system is to consider the concept of positive trust balance. Positive risk balance has to do with whether you think your system is safer than a human driver. Positive trust balance is whether other stakeholders trust that your assessment that you're safe enough is really true. In other words, stakeholders trust that the lifecycle risk will be acceptable. There are 4 main pillars of positive trust balance. The first is engineering rigor. The next is doing validation. The third is having field engineering feedback. And the fourth is safety culture. Another way of framing this is that to achieve positive trust balance, you need to build it right, test it right, improve it right, and live it right. Ultimately, successful deployment of autonomous vehicles will require building trust with stakeholders, including especially the public. Building that trust will require safety transparency, as well as approaches that go beyond pure testing-based validation. To achieve transparency, companies will need to achieve a positive trust balance, which includes rigorous engineering, strong validation, safety-critical field feedback, and above all, a robust safety culture.